can't see it somehow. Okay. You can see the available expressions, right?
Yes, looks good.
Okay. All right, folks, let's get started. Quick announcements first, and then we'll get going. The first one is we have assigned the next homework number 2, which has 4 problems. This homework is going to be just a paper and pencil exercise. It's not to be implemented in LLVM or anything. So we are giving, of course, a couple of weeks here, due on next week on Friday. And it's an interesting homework which will build on what we have been covering here, and we'll ask you to work out several things, algorithms, and show the examples. So hopefully it will help you to really understand these concepts which we are covering in terms of data flow analysis, and sort of get those covered well. There is a PRE problem at the end, which is the topic which will hopefully start either today, later today, or latest definitely on Wednesday. And that is the advanced data flow analysis, which is a little bit more involved, but we'll build on the concepts that we are already looking at. And then the other parts of the homework are about safety conditions for available expressions. We have done the safety conditions for reaching definitions. So we are asking you to do that for available expressions, which is a topic which we started last time and which we'll finish now. And we'll go further from there. There's also on the very busy expression, which is an interesting analysis, and whether it's legal to hoist it or not. That's a more important part of it. And I believe there's one more problem there in terms of, I mentioned PRE, very busy expression, the available expression. And the last one that I wanted to talk about was whether the use of a particular value is sound or unsound. So if one of the reaching definitions there involves an uninitialized definition, to a given use, then it is unsound. And what happens is because of this, this could propagate further. It could generate unsound in-turn definitions, and they could generate unsound uses transitively. And there are 2 parts to this. One is to write a data flow analysis from scratch without assuming anything is done, towards capturing only these sets at the entrances and exits of the basic block. Again, this is all on paper and pencil. So you have to write algorithms, you have to show the examples and so on in a very detailed way as asked in the example. And the other part of it is involves what is the effect on branches, and whether still some of the execution of the program can proceed in spite of this unsound stuff. In the sense, will it still be legal? In terms of control flow, of course, the data flow will not be correct, because obviously it will lead to some execution, and some control flow may be messed up. And because of that, corresponding data flow might also get messed up for the execution of a basic block. But in terms of control flow, whether it will still allow certain basic blocks to execute without jeopardizing them in any way, That's the idea. So go through this, read this carefully, and you can get started. I believe you can get started on the available expressions, unsound uses and definitions. And from there, I believe the PRE is the last problem, so we'll wait on that. Once we cover it, you can do that, but don't wait on the other parts. These two, and what was the third one? Very busy expressions, which we'll be covering also today. And it's pretty nicely self-introduced there in terms of what exactly it is. So that's about that particular part. The second thing is we are getting ready to give the project part 1. So again, an announcement, please pair up teams of 2 students. I think I checked the enrollment in the class, so we may have an odd number of students. We'll allow a team of 3, but only one team. Or if somebody wants to go solo, which is also fine with us, and then we'll have just teams of 2. So do the pairing using the Piazza teaming feature, and Nathan will monitor it, and let's get everybody in teams in a couple of days, because we'll be ready to assign it, I think, on I would say by Wednesday for sure. Okay, so let's get back in start where we left it off. I'll pause and ask some questions, and you can also do the same. So don't have to wait for me. If something is not clear, just raise your hand. We were looking at available expressions, and I'm going to continue that discussion. So the whole idea here is, of course, some expression is available at a given program point P if from entry node to that particular program point it is computed, and there are no redefinitions of X and Y since the most recent occurrence of that expression on that particular path. So as you can see, this was also similar to the copy propagation, because copy is a particular type of an expression, X is equal to Y, and the operator there being equality. Here it is just plus, minus, star, or whatever. So what is the whole idea behind finding out available expressions? So if an expression is available at a given program point, it need not be recomputed, and it can be, its value can be reused, and if it's there again computed, then obviously it is redundant, can be removed. And very commonly this optimization is called as common sub-expression elimination, and it's one of the most important optimizations, because a lot of array calculations, the index expressions for finding out the offsets, they are computed very repeatedly in loops, and even if it could come out of 2 different arrays, let's say A of J and B of J, where A and B are 2 different arrays, you can see that the index expression involves J and is common, and therefore can be eliminated if it is redundant. So that is a very, very common usage of CSE. And similarly, the same analysis, as you know, can be applied towards copy propagation. I had mentioned last time that if you eliminate a copy, you have reduced the number of active entities present at a given program point, and therefore you could reduce the register pressure, because you can only have so many registers, so you don't want to keep redundant values which are exactly equal to each other in a register. So Copy propagation, of course, allows you to get rid of whatever has been copied from one name into the other because of equal to operator and same analysis as CAC. Of course, what it does not capture is what we call as value redundancy. In other words, A and B, two different variables, might be exactly identical in terms of value they carry at a given program point P. But A and B may not be exactly generated through A equal to B or B equal to A operation, and therefore this analysis will not capture those cases of A and B being exactly identical in terms of value at a given program point. Now you may ask me, oh, how can we generate this without generating copies? Think a little bit more. There are several examples of where A and B could be equal in terms of their value, but need not be generated by an explicit copy operation such as A equal to B, etc. So we'll cover that case, what is called as value numbering analysis, in the local sense, in a basic block, as well as in a global extended sense across the whole program, whole procedure, using a SSA based representation. So we'll wait on that particular part. But for now, we'll cover both CAC as well as copy propagation through this. So this particular definition is, of course, the operational specification of how the expression becomes available. Again, we don't want to take an approach here of generating or enumerating all these paths and then finding out if these conditions are true, and then therefore detecting if something is available. We want to break it down in terms of the data flow equations and expressions and so on. So here are some simple examples which just quickly show what is going on and something if it is available or not that. So you can see that it's a simple flow graph coming from top to bottom, and then let's assume that's the root of the program. The first basic block starts execution there. At the end of that basic block, you can see that A plus B becomes available and remains available so until the point of A is equal to A plus 1, because then the operand is getting redefined and so on. So whenever you hit an execution point and thereafter, unless the operand is redefined, it remains available. That is one part of it. Second part of it is you can see for the similar reasons A star B will be available, and then the third one will be A plus 1 after that particular point will become available at the execution point after which it is generated and so on. So so what really is going on here is at a particular point, an expression, it is very similar to the gen set in terms of a reaching definition, except for the difference that in one case it is a definition which originates. In the second case, it is the expression which is getting generated. So A plus B, A star B, they are getting generated at respective points. And then you can see that correspondingly, once they are trying to get through a particular basic block, again in a very similar way as reaching definitions, one of the operands, if they are redefined, then they are getting killed. So you can see here a simple example, plus B being generated in the first block, A star B being generated in the second block. They are not available, or they are not there before the respective generation points. And then once they originate in a given basic block, they continue till the end of that block, unless one of the operands were to be redefined. So in this case, of course, there is no such thing as A being redefined in the first block. or in the second block, or B being redefined in either one of those blocks. So those expressions will continue or will become available at the end of the blocks. They could also be, just like regions, are downward exposed in the direction of flow. Similarly, these we could also call as downward exposed expressions. That is, those expressions which are evaluated, but after the evaluation point, there is no redefinition of their operands in the given basic block. So if you filter those expressions, they are the ones which are generated there. Coming to kill sets, they are very similar. If one of the operands is re-evaluated, and you can see that that will kill the expression which is coming in. And the definition of kill here will be also same. We'll assume that every expression is available everywhere. And if one of the operands is redefined there, we'll get rid of it just by using its kill set in that block. Whether or not, of course, it is reaching will be or whether it's available will be defined by the data flow properties. So here is how the available expressions therefore could be computed on a local basis. The first A plus B will become available after that statement. It will continue to become available at the next basic block. Then A star B will join there. You can see that it is generated there without any definition. And then if we go to the next basic block, what will happen is we will have continued A star A plus B, for example, coming from the top, going to the entrance along that edge. So that is where it has been propagated. But now we'll apply the definitions of what causes the expressions to become available or not, proceeding further. So at least we are going top down here, and we are just trying to propagate it top down. Here you can see that because of the redefinition of A, both are blocked and not going forward. And again, there is nothing going there in terms of the next basic block. And here A plus B is regenerated in terms of the expression. So going back to the basic block where we will reevaluate the available expression set. You can see that there's a back edge between the last basic block and the other one. And we are getting here on the forward edge that we had processed from the fall through edge. We had A plus B and A star B coming in. On the back edge, though, we only had A plus B because A star B was killed there, as you can see on the down path. So A star B is no longer coming back through that back edge. So that's what makes the entrance of that Y greater than A basic block, only A plus B is available. Okay, so again, the expression has to be evaluated on all paths, and after the evaluation, there should not be any. So if you apply that, A star B doesn't satisfy that, and therefore is not available at the entrance of the Y greater than A path, although it is available on the forward edge, which is that particular edge. But of course, we are going to compute all these values in all the data flow problems that we are looking at, except very, very few ones. the PRE being one of them. We are going to compute all the data flow facts at the program points which are in the beginning of the basic block, which are inside the basic block, and which are at the exit of the basic block. We are not going to compute on the edges. Therefore, A plus B continues to be the available expression because satisfies these particular criterion. And then iterating further, it is not getting killed there because there is no redefinition, and A plus B continues to be the available expression over there because of this reason. So the correct final set of expressions which are being computed here is being shown on the right hand side. And so A star will not be available at that particular point. Only A plus B will be available. And then A plus B will propagate and so on. So this problem also satisfies exactly the same similar characteristics. It shares it just like our reaching definition problem. It merges the data flow fact at what we call as a join point, where two or more branches meet together, and it is also a forward problem. In other words, an expression is generated and then continues or becomes available from there onwards. And unless it is available on all incoming edges of a basic block, it is not available at a given point. So the property must hold good on all the incoming edges to a given block. So the essential difference between, there are a lot of similarities here between reaching definitions and this analysis. First of all, both are forward, both propagate through the basic block exactly in the same way. However, when we join them at the entrance of a given basic block on incoming edges, they are very different. Reaching definitions is union. That is, if a definition can reach along some path, it is reaching at a given point. Whereas availability of an expression is it must hold on all the paths that are joined, and that's why it is a intersection operator here. There is a union operator there. So here is the data flow equations or transfer functions, which are inset of a given basic block is intersection of outsets of the predecessors, and the outset of a given basic block is the gen set or the downward exposed expressions union with whichever was coming in as available and whichever is not killed. So exactly similar type of problems here, except for the intersection operator. And that is why both the problems are in the forward direction of the data flow. The one other thing before we sort of go off from this particular available expressions is that the way the algorithm works is slightly different in terms of initializations. The reason here is what we want to compute. Let's look at the safety condition here first, and then we'll see what should be the right way to initialize this algorithm to be able to get the correct answer. So you can see first of all that the way we will use this particular information about available expressions, as we showed last time in the slides, is that if a particular expression is available and there is a evaluation of that expression in a given block, then the second evaluation in a given basic block will be redundant and will be eliminated using the available expression. And we'll evaluate the expression at its original points. We'll hold the values in some temporary name, and we'll substitute them at the second expression, which was redundant. That's the way we will do the optimization. So now let us look at this particular condition in terms of what is the safe set of expressions that we must somehow generate. So let's say if we had some oracular way of evaluating these expressions for whatever are the expressions become available. Let's call that set is E actual, the set of expressions which are available at a given point, E actual, whereas the set what we find is E found. So you can see that somehow if we had E found as a superset, if it had even one more expression which is not present in E actual, let's say some X star Y we have found as available expression. Why did we find it? Maybe some bug in our algorithm, some wrong way to do it, whatever. But somehow if we find one more expression which is not really there, which is not available at a given point, and if we use that to carry out CSE, if we remove some expression X star Y based on this, you can see that there will be a problem because the values of those two expressions may not be identical. That expression may not even be evaluated before we come to this point, something like that. And because of this, we will end up doing a wrong elimination here. So we cannot have a superset. So at best, for highest precision, we can have a equal to set, but obviously we will not be able to find equal to set for exactly similar reasons as we saw in terms of reaching definitions. So what were those reasons? Lots of approximations that we are introducing here in terms of program paths and things like that. Imagine an infeasible path along which there was no evaluation of certain expression E. But we assume that it is feasible in our analysis because we can on infeasibility statically. Since we assume that path is also feasible and there was no evaluation of E on that path like X star Y, we remove it from the available set of expressions along that path. In actuality, it will be available because that path will never ever be taken, which has maybe some redefinition of X or Y, things like that. That path will never ever be taken, and so expression will be available there. However, we cannot rule on this, and therefore, using the definition of all paths being feasible, etc., we assume that this expression was not available, and therefore we did not do any optimization. So in order for this particular strategy to be correct, we must find a subset, and that's what we do. So in short, because of the approximation that we introduced, one of them is paths, second is pointers, all these kinds of things. By the way, the second one is a part of your exercise, which you have to do to find out and get a feel for how we end up losing certain expressions, which may be available, but we cannot rule on them as available. So the safety condition here is E found must be a subset of E actual. E actual being the actual set of the expressions which exists at a given point. If we had an oracular way of computing it, if we had a perfect knowledge of all the program's behavior in terms of its pointers, in terms of its paths, in terms of all the actions, if whatever we introduce, they were to go away. And with the perfect algorithms, if we find that, then that will be actual. And E actual is a superset. What we find is a set of available expressions is a subset typically. At most, it could be equal. And that's the safety condition which we must operate under. You can see that this safety condition is very different than the reaching definitions. In case of reaching definitions, we must find a superset for being safe there. Here we must find a subset for being safe. So with regard to this, how do we therefore maximize the precision of our analysis? So you can see the satisfying solution to the safety condition. We could take a very easy approach and say that, hey, nothing is available anywhere. And we can that as the initialization point, that nothing is available anywhere at the inset, and then compute from there. But that's not what we do. We start, we want to maximize the precision here. So we want to find that set, assuming the analysis is correct. We want to find that set which is maximal here, which meets these constraints. And therefore, the initialization condition here is, we said that everything is available everywhere at the entrances of the basic blocks, and we iterate from there. And you can see that because of the intersection operator, we are going to slowly reduce this set as we go further in the analysis, and in the steady state, we will have the correct solution, which will end up as the maximal solution to the set of equations. So contrast this initialization with the reaching definitions. The reaching definition insets were assumed to be null. Here, the insets are assumed to be including all the expressions which are assumed to be available. And so that's why the big difference in the initialization of the two. And that is to maximize the precision of what we are trying to find out, and it's consistent with the intersection operator. So that's as far as the nuances of these, and you will see some more as you do the first problem in the in homework, which is really asking you to find out the safety conditions on and the role of pointers in terms of finding out these sets. So let me from here touch upon a particular topic which is important a little bit historically. This analysis is not done much these days per se, for the reasons it was going to be there, but has manifested. The use of this information is manifest in a slightly different form. What is this analysis, and what is this particular concept here? Before we jump into that, are there any questions on available expressions in terms of any kind of thing which we discuss so far? As I said, again, the available expression also includes copy. So if you generate A equal to B, which is downward exposed, and A is equal to B, will propagate the same way as an assignment operator, which is on all incoming and get intersected, and then it will flow through. If A or B were to be changed in a given basic block, A will equal to B will not survive as a available expression till the end of the block, and again it will get killed, etc. So exact same analysis, and therefore with that analysis we will overcome the limitation of directly using the reaching definitions and trying to infer from there if we should do substitution. Reaching definition was inadequate because it didn't account for modifications due to B in the path, but here this does account for that. So if there are no questions, then I think we can move further. So very busy expressions was a very historically important analysis. The main goal in terms of the analysis was um, to reduce the code size and like the performance. So what is a very busy expression? So very busy expression is defined like this, that we are at a given program point P, and no matter which way go from this P, will go down, of course, in multiple directions we could go. No matter how we take these paths, on every path we will be evaluating E, and between the current point P and the evaluation point of E, we will not have any change of any operand. Okay, so if x plus y is we are looking at, from P we'll be going down on one path, and we'll encounter the x plus y on that path before we encounter any redefinition of either x or y. Similarly on all paths. So if that is the case, no matter which way we go, we are going to find the evaluation of this particular expression sitting on all different paths from a given program point. And we basically call such expression as very busy expression. And why is it important? It is important because along those, since E is getting evaluated anyway, the question is, can we put this E at point P, and because of which we can save on the evaluation of this E at different downhill program points. In other words, can we hoist it up, and we can save on space here. You can see that we will not be doing any redundancy elimination. We will not be doing any avoidance of re-execution, etc. But we're simply trying to move the evaluation up, and we will avoid unlike maybe 10 different codes for evaluating this. If there are 10 different paths on which E is getting evaluated, we'll try to evaluate it only once, and we'll save on space there. Now you may ask me, oh, where does this really originate and things like that? It does occur even in modern compilers cases, these type of situations, because you may have function calls which may be replicated across all these branches to inlining and so on, and they'll generate very similar expressions which will sit across all these different paths, and it will be a good idea to move them up and save on space. So the question is, this type of problem that you're looking at here, what is the data flow, what is the nature of the data flow problem here, and whether it is a forward or a backward problem, whether it is a may or must problem, that is it similar to the available expression, but in a backward sense, and so on. So this should remind you of what you saw earlier in your earlier compiler classes, which is what we call as a liveness problem. So I'm just going to touch upon this and not get into liveness right now. But liveness problem is exactly like this. What we are looking at, and there is slight difference between liveness here in terms of the information that we are interested. So liveness problem asks us a question that is a variable v live at a program point P. And the answer to that question is if it is used along some execution path starting with P, it is live. That is, if we go along some path from P, and if there is a use of this V over there, then V is live at the program point P. Of course, this is about some path. It is not about all paths. So this is the main information here. And want to find out if V is live at this point for what? because if it is live, we may consider keeping it in a register. If it is not live here, however, it is along all the paths, there is no use of this V along any of these paths. V is not live in that particular case. Obviously, it is not even a candidate for being in a register. So this is the liveness problem. You must have seen this because the code generation has to tackle it. 40 to 40, we do that analysis, liveness analysis. And in order to determine if something is live at a given program point, we have to find out what is going on downhill, and then use that information to decide whether something is live at a given point or not. And that is the nature of the problem that we really solve, looking at the information downhill and using it uphill to decide whether it is live or not. And similarly, in this particular case, so liveness is a backward problem, as you know. We look at future uses and find out if something is live at a given point. And in a very similar way, we had to, I will skip the details of liveness because that's something which we have done in our undergraduate studies. And when we talk about register allocation in backend, we might revisit it. But for now, focusing on very busy expressions, the definition of the problem is very, very similar. That if E is evaluated on all paths downhill before any of the change of operands, then E is very busy at P. So in order for determining whether E is very busy at P, we must look downhill, and therefore that's a backward problem. So the information which about E, which we glean in downhill paths, whether E is evaluated or not, is useful in determining if E is very busy over here. So this is also a backward problem. The difference between liveness and very busy, however, is that in case of liveness, we want to find out if it is used along some path. And so if it is used along some path, then it is live, and that's the main information. Whereas in this case, an expression is very busy if it's a must information, that is, it is evaluated along all the paths. So so a lot of space reduction, as I was saying, was the goal of this. And how do we formulate this particular problem? Again, let's look at it. And that's something which is very similar to the available expression, but in a backward sense. So what we do here in terms of determining if some expression is very busy is you can see that first of all, in a basic block, we look at it and see if it is evaluated. And in this case, remember, we are moving backwards. So the difference between available and here is that this particular expression must be upward exposed. In other words, if we look at a basic block and look at x plus y there, between the entrance of the basic block and the evaluation point of x plus y, we should not have any reassignment to either x or y. In that particular sense, this will satisfy the definition of E being now very busy at the beginning of the particular block. So that's what we start with. We go to each basic block. And these could be called as gen sets for very busy expressions, which are computed in a backward way. In other words, we look at whatever are the upward exposed expressions in each of the blocks and collect them in their insets. So that is one part of it. The second part of it is pass-through, just like available expressions. So how do we determine pass-through? So let's say some expression was very busy at the exit of the block. and we haven't redefined its operands in the basic block. And that's why it will continue to be very busy in the beginning. So the expression which is very busy at the end, at the out, which is not killed in the basic block, will remain very busy at the beginning. And that's how we determine the pass-through part of it. So we have gen, then we have pass-through. So that defines the movement of an expression through the basic block. And now across the basic blocks, you can see that we are going to take, if something has to be very busy at a given exit of a block, then what is the condition here? It must be very busy at the each one of the successors entrances. Because if it is not busy, then it doesn't satisfy this path condition that it's a must condition. So we take the intersection operator. So whatever is the very busy at the entrance of the successors insets, we collect those, take their intersections, and that determines the very busy set at the exit of a predecessor. And that now we have covered all these three things: pass-through case, generations case, which is upward exposed expressions. Those expressions which are seen from the entrance of the block before any of their operands are redefined and which are generated in the block. So those are upward exposed ones. So we collect all these we start the analysis with the upward exposed ones by initializing these sets. And again, in this particular case, because the operator is intersection here, we will start with a universal set because we want to kind of keep the precision of the analysis as high as we can. And that is the outsets are all initialized to every expression being allowed to be very busy everywhere. So that's how we'll start. And slowly we'll reduce these sets because of the intersection operator in a backward sense now, although we'll iterate and again we'll converge. So the initialization condition is very similar to available expressions. Because the operator is the intersection, and of course the analysis is backward, and the differences here are also in terms of upward exposed expressions participating in the as against downward exposed expressions participating in the available expression sense. The pass-through conditions are the same, and the operator is also intersection. So we'll iterate in similar way. We'll keep going backwards, and we'll converge, and that way we'll find out the set of very busy expressions at a given point. By the way, these expressions in the old terms used to be called as very busy expressions, which was sort of, I think, the term used by compiler writers to find out, hey, these are sort of the big problematic ones for code explosion, and let's reduce them. But in modern terminology, which we'll use in PRE also, these are also called as anticipatable expressions. So we'll use this terminology interchangeably. What is an anticipatable expression is same as very busy expression. That means that if I'm standing at a given point in the control flow graph and looking in every possible direction, I'm anticipating that I'm going to evaluate this E, and that's the reason why this is also called as anticipatability of an expression. I'm going to definitely run into the evaluation of this expression before any of these operands are redefined. So that is why it's also called as anticipatability of an expression. Now, of course, the big goal of very busy expressions analysis, after we kind of do all this analysis, is to figure out how we can get rid of evaluation of this expression from multiple points downhill and hoist it up at a highest point, wherein I will have just one evaluation, and I can get rid of maybe 10 evaluations from the downhill point. Because of this space reduction it occurs. That is the big use of this very busyness in terms of um, use of this information. Now, big question is, can we always do it? Maintaining correctness of the program, and that's something which you have been asked to do in your one of the problems in the homework. Then let's assume that we detect that, hey, an expression is very busy at a given point. Can we always move it to that point that and get rid of all the downhill executions of this expression? Or is it sometimes we can do it, sometimes we cannot do it? And what is it that we must watch out for? And I will let you, of course, give thought to that, whether it is always safe or not, construct different examples, think of what all could happen there in terms of um, very busy expressions not behaving the same way as after the original point. Of course, I implicitly mentioned here that the available expressions, on the other hand, are always you can replace them at the point of availability. We can move them from the original point to the point of where they are available, and that's why we can get rid of the redundancy as I was pointing out. Second instance of x plus y, we could get rid of it. And we have the execution of x plus y that happened earlier, and we can take its value, store it in a temporary, and use it at this x plus y point. And that is always possible, whereas I wanted to give thought whether this is possible in terms of of an expression going backward things. So here is a summary of some analyses we have seen, which is classified as backward, forward. And there are many analyses, of course, which are may and must possible information also. Reaching definitions is a forward analysis with may information. Available expressions is a must analysis, on the other hand. That's the operator being intersection in the forward direction. Backwards direction, very busy expressions is a must analysis. And in the backward sense, may analysis is live variables. Most of the analysis we can classify as forward and backward, and may or must. But there are some which, at least there was a belief that there were some. One of the most prominent beings partial redundancy elimination. Whether it was a bidirectional analysis or not, that means you have to simultaneously solve the equations. The word simultaneously is the key here. That you have a set of constraints, like in these different things, and you have to simultaneously solve and meet the constraints in both directions at the same time. And therefore, the analysis could be very, very complex to carry out. The solver has to work in both directions at every point of refinement of the solution. And that was a belief earlier, but it was not true, as we'll see in just a little bit. But there are still some problems like type analysis, which is a bidirectional problem. Type inferencing is a bidirectional problem, which you have to solve simultaneously. Otherwise, the solution is not correct. So with that, what is a modern way of writing the data flow analyzers? Of course, we can construct these particular all these facts in terms of what we call as lattice. And lattice, some of you might be familiar with this concept, which is an algebraic entity in which least common properties and greatest common properties, they are being used to sort of designate what happens here. So for example, if you have different expressions here, what is common amongst them is none at the bottom level. And what is the unification of them, which is the top, which is all three of them. And in between, of course, pairwise, they could be having something common, or individually they could just sit there and so on. So this defines a lattice of all different properties of algebra, which think about relationships between these operators. And we can model this problem using these lattices to solve the data flow equations, which were shown earlier. The formulation is, of course, the same, but the solution could be using lattices here. And in general, all these lattices and these data flow equations, they define what is called as a partial order, such that it is reflexive, antisymmetric, and transitive. This is more about theoretical implications of these. And using these lattice properties and the partial order, we start with the correct seed, depending on the precision that is intended for the problem, and we'll solve it, and we'll get the solution which is satisfying to this relation here. In that particular sense, this is also called as meet, or the greatest lower bound of an operation, which is formally defined here, which I don't want to get into because I think it's more about just the formalism. The other one is also called as least upper bound, or a join, and which is also more formally defined. But and then there are a lot of lattice properties which are typically formalized in terms of top, bottom, etc., etc. So I'll just leave that particular part. But mainly the data flow algorithms all work in the forward-backward sense, as we talked, in the iterative sense, using the bit vectors, and they preserve what we call as monotonicity in terms of the different operators intersection or union, and they also terminate because finally they converge to a lattice which has it at the top or bottom, and it has a finite height, and we end up doing this movement of a particular element in a particular unidirectional way, depending on the problem, going from, let's say, top to bottom or vice versa. And there are finite heights of these lattices, and therefore each one of the statements goes through finite number of states in a monotonic way. Most importantly, it doesn't fluctuate from one state to the other and again goes back to the original. And that's why there is a termination guaranteed. So these are a little bit more formal parts of this, which aren't that sort of importance. So let me switch the gears, and I will, if there are any questions on this, we'll take, otherwise we'll move to our next topic, which is loop invariant code motion and partial redundancy. So are there any questions about any of the basic data flow that we have done so far, reaching definitions, available expressions, or very busy expressions, or even for that matter, liveness? We haven't covered it formally here, but we'll revisit it, as I said before, touching some more advanced register allocation things, just to refresh ourselves a little bit there. But if there are any questions on any of these algorithms, their safety conditions, initializations, or any of these things, we can take those now, or otherwise we'll move to the next topic of loop invariant code motion and then PRE.
Nothing here on the chat.
Okay, I'm going to now share just a minute. Are you guys seeing the partial redundancy elimination, loop optimizations, lazy code motion?
Yes.
Okay. So now this is the last part of data flow analysis, which is based on what we call as bit vector analysis, traditional analysis, but which is sort of pushing the limits of optimizing things, especially for carrying out certain important optimizations the way it was traditionally done and the way it is being done now. We'll look at both of the angles, and then we'll the next the SSA, wherein the IR itself is changed, and we'll be leveraging certain properties of the IR. So let me get into some of the things in terms of especially optimizing the loops and what happens there, and what was the traditional way of doing things, and how we optimized it in terms of doing certain things in a different way. So let's quickly recall redundancy and what was going on in terms of getting redundancies. That here is an example of B plus C and being evaluated on both sides, and there is a B plus C again being evaluated. So you can see that B plus C was available there at the point of join here. And in this particular case, we could get rid of this B plus C by using the evaluation of this B plus C here or at the top. However, that may not be the case always, that it may not be fully redundant. And it could be that it is what we call as partially redundant. And those are the cases which we are going to have to worry about how to deal with them. So if you see it in the red here on the right hand side, it is not redundant with regard to this expression, because B plus 1 is being redefined, etc., from this point onwards. And deal with the implications there. So what will happen is, suppose something is not totally redundant. Let's say it is redundant on coming from this side, it is redundant, and left side and right side, it is not redundant. Then what are we going to do? And we will really have a problem if we leave something in not really take care of the redundancy in this particular respect. So can we do something, first of all, um, for this partially redundant expression? And what is it that is partially redundant? So we'll continue this example over here in this slide now. You can see B plus C is available on the right hand side, but it was coming in into before this B equal to B plus 1. It was available there, but because of this redefinition of B, it is no longer available after that point. So, so the downhill B plus C that we see at the join, we cannot eliminate it because it is partially redundant. Now you can see that on this side, it is redundant. So if we come in through here and if we don't do anything to this B plus C, then we'll have a redundant execution here. But if we come on the left hand side, of course, we won't have any redundant evaluation there. So can we do something about this? The answer to that is yes. What we can do is we can cover this lack of evaluation of B plus C on the left hand side by putting an evaluation of B plus C on the left hand side here. As you can see, B is equal to B plus 1. After that, we have A is equal to B plus C. We have put an evaluation there. And we have evaluation, of course, A is equal to B plus C on the right hand side, and that makes it redundant at this lower join point, and we can get rid of it. So we are able to what we call as cover the non-redundant parts of the expression by putting something over there. Now, so far, as you know, in any of our examples, we did not really carry out any as such insertion of some expression. All we did was, of course, in available expressions analysis, when it was available on both sides and it was detected as redundant, we simply got rid of the redundant one. We did not carry out any insertion. In this case, we have no choice except to do an insertion to be able to cover this expression. And that's a little tricky business, especially what we don't want to happen is that in getting rid of redundancy, we ended up adding something which led to some inefficiency of execution in the program. And therefore, we had to watch out for how we do it, where we do it, and so on. And that is one issue which will dictate what we'll do with this redundancy. Now, why undertake all these headaches? You may ask me this question that, oh, insert somewhere here, get rid of it there, make sure that it is not adding something, but it is only reducing something. There is a reason for that. It wasn't just like fanciful theoretical work. Compilers, there is some of that, but not a lot of it. Most of the work is driven by real practical cases. And here is one case which is really prompted of what we call that the partial redundancy being solved here as a problem. So look at this example over here. On the left-hand side loop, if we run, so this is B plus C, this particular expression, A is equal to B plus C, is executing inside the loop. Okay, agreed. It is constantly executing millions of times perhaps. And you can see none of the operands, B or C or for that matter, A is being computed out of those, is really changing in its value. So whenever the loop executes, you will see that it will exactly maintain the same value over and over and over throughout these million executions. And however, if this expression is an expensive one, like exponential chain operation or some division or something, it will cost a lot to evaluate it inside the loop. Now, if you look at it very carefully, it is basically what we call as a loop invariant. In other words, the value is not changing at all. And we want to move it outside, first detect it that way. And you can see that across the iterations, it is really redundant. But we cannot detect it as redundant using our original available expression analysis. Why? Look at it very carefully here. In order for getting rid of this B plus C, we should have some B plus C's evaluation where that X is equal to Y times Z is sitting. We should have some evaluation there. So B plus C will commit as available expression here on the incoming down edge of the loop, entrance edge. And then B plus C is loop generated and will feed along its backward edge over here. Now intersection of these two will mean B plus C is redundant, and that's how we'll get rid of this B plus C, and everything will be voila, nice. But in this example and many other examples, that's not the case. You can see B plus C is not coming in on the left hand side of this example as an evaluated expression. So it is not available on the top edge, which is the drop-in edge of the loop. However, it is being constantly generated and used again and again in things inside the loop. And in that sense, it is redundant. It is certainly could be pushed out here in the top level. X is equal to Y plus Z times Z. It could be pushed out like that, what is shown over here at the top level, and we could get rid of this expression and the loop could be transformed, as you can see on the right hand side. So if we had somehow had a way of getting this loop invariant detected inside the loop, we could easily push it out into the pre-header of the loop, execute it only once, and save a lot of computation inside the loop body. However, the problem is our redundancy detection, which is supposed to be doing this, the available expression redundancy detection current framework is not detecting it as a totally redundant expression. If somehow we had B plus C in the pre-header, if it is existed, then we would detect it, but not otherwise. And this will be detected as a partially redundant expression, however, because it is not redundant on the top edge, but on the back edge here, it is available. And so it will get detected as a partially redundant expression. So now what to do? So there was no known analysis for partial redundancy elimination then. Only availability analysis was present. And we had lots and lots of cases of these loop invariants sitting inside the loop, which needed to be moved out into the header of the loop and so on, pre-header of the loop and so on. So ad hoc techniques then were generated in the meantime. So people knew about this problem. The researchers knew about this problem of partial redundancy being a very important problem. But there were no solutions to these, and we'll see why that was the case. It was supposed to be a hard problem of data flow analysis. This was supposed to be what we call it bidirectional data flow. And so there were no solutions known, and therefore ad hoc approaches had to deal with this somehow, figuring this special case of analysis and so on. Now you might say, oh, what's wrong with special case? Well, loop invariant code motion is very, very, very important optimization. And if you have one particular analysis which deals with one type of optimization, another analysis deals with another optimizations. First of all, your code bases grow. You have to debug them. Compiler is one thing, which if you have a bug, then it will create a total havoc. And there may be unpredictable interoperations between these different phases. So in short, for software engineering reasons and otherwise, it is better to have a unified analysis which tackles all these different special cases. This is a special case, as you can see. Loop invariant code motion, the way I showed it, is really a special case of partial redundancy. When it occurs inside a loop in this particular peculiar way, it is the case of loop invariant code motion. When it occurs in general, that's a case of partial redundancy, as we saw in the previous example, where here there is no loop, nothing involved, but we could get rid of this redundancy in this way. So this being a special case, and it was known that it is a special case, but no analysis was prevalent for partial redundancy, and so they had to develop a solution to deal with this special case in a special way. And you will see that when we do it next time, this solution is pretty ugly, and it really captures very specialized behaviors that may occur inside the loop and so on, and relies on some ad hoc information. And so we'll see that solution first, about how to detect what is called as a loop invariant, and then how to, more importantly, detection is the simpler part, but the motion of the loop invariant, moving it out into the pre-header, that is a tricky part. And that is where PRE really steps in terms of both, of course, detection as well as motion. But in the absence of PRE, we develop some ad hoc ways to decide whether it is safe to move this particular redundant expression into the loop header. And that had to analyze a lot of properties of what is going on with this invariant. Again, detection was the easy part. Detection of PRE is also easy part. That's not the big problem. We know that it is available along some edges and it's not available along some other edges, and that's partially redundant. There you go. That's not a difficult one. How do you get rid of it? How do you use it for optimizations? And how do you use it for loop invariant code motion? Those are hard problems. And without the solution in PRE world for optimizing getting rid of partial redundancy, we resorted to the ad hoc approaches for loop invariant code motion, which we'll see. So first we'll deal with loop invariant code motion the way it was in a historic sense before the advent of PRE, both detection as well as code motion. And then we will talk about PRE, how it subsumed both of these analyses into one and more. And we will then talk about how the modern PRE has come into being, skipping a lot of history here, because in between it is extremely, extremely complex and very difficult to understand, which I'm not going to expose you guys to. Fortunately, we have what is called as a very clean formulation of PRE, which we call as lazy code motion. And we'll look at that by Jan Snoop and Dreckler. Those two papers I have, by the way, put there. But first we'll start with the loop invariant code motion in terms of detection, and then in the second in terms of remediation, of how to get this out. So we'll stop here and see you guys in the office hours. Thank you.